Hi, myself Kaushal Limbasiya. Today I will present on OpenACC. So, OpenACC using GPUs, whether in your laptop or in a complex hybrid supercomputer, is just difficult. It takes considerable efforts to program for GPUs. OpenACC is one method to program GPGPUs, General Purpose Graphics Processing Unit, also known as GPUs. So, what is ACC? ACC is a software accelerator that offers portability between the compilers. It was first developed by Cray, CAPS, NVIDIA, and PGI. It is designed to simplify parallel programming on heterogeneous CPU and GPU systems. OpenACC can be implemented in languages like Objective-C, C++, and Fortran. It works with different accelerators like NVIDIA, AMD, and Intel. There are also compilers like PGI, CRAY, and GCC that runs OpenACC. Talking about the history, so OpenACC was demonstrated at Supercomputing Conference in November 12, 2012. It was officially released later in June 2013. OpenACC has its own specification and it is organized by OpenACC members, which includes AMD, NVIDIA, CRAY, and Oak Ridge National Laboratories. So these members are the permanent members of OpenACC. The latest version of specification 3.0 was released in November 2019, where first was released in June 2013 as talked before. Apart from these members, there are also other members which organize OpenACC. Let's talk about the OpenACC accelerator model. In the OpenACC execution model, the multi-core CPU is treated like an accelerator device that shares memory with the initial host thread. With the shared memory device, most of the OpenACC data clauses are ignored, and the accelerator device uses the same data as the initial host thread. When using OpenACC with a GPU, data gets copied from the system memory to the device memory and back. The user is responsible for keeping the two copies of the data coherent as needed. When using OpenACC on a multi-core, there is only one copy of the data, so there is no coherent problem. However, the GPU OpenACC program can produce different results than a multi-core OpenACC program. This occurs if the program depends on the parallel compute regions updating a different copy of the data, whereas on a sequential CPU program, the data would be updated by just the host. Let's talk about how to accelerate a code with OpenACC. So firstly, profile and identify hotspots. So first we need to identify our computational hotspot. This can be done by profiling tool. Second, analyze your code. So we need to analyze our code for the parallelism. So particularly the hotspot that we defined in our first step for possible parallelism. Third, we need to add directives. So add the correct OpenACC directives around your hotspot components. The choice of directive will depend on the component identified. Fourth, it is important that you benchmark your code, that is computer serial and parallel performance. All performs of parallelism, whether using OpenACC or GPUs or any other tool for any parallel computing architecture introduces overhead. It is therefore important to make sure that what you have done is actually improving performance. Good benchmarking and reprofiling of your code can help you implementing more efficient parallelization. Last, optimize parallel code. Having benchmarked and reprofiled of your code, you can then optimize by improving things such as data locality and minimize data transfer between host and device. Today I am going to parallelize matrix multiply using OpenACC. So to use OpenACC, you need three key components: a compiler designation, a sentinel, and a directives. The compiler designation, a pragma in C, or an explanation mark in Fortran, informs the compiler of something about the code. In our code, the hash pragma is a designation. The next component, the ACC sentimental, that tells the compiler that following text will be OpenACC. The following sentimental, the sentinel is the OpenACC directive. The directive may be executable statement or influence one line or a region of code. These directives may have clauses, but all must follow the syntax as laid out in the OpenACC standard. So in C, OpenACC directive starts from hash pragma C, as we can see in our code. This is followed by directive names, that is parallel loop is the name of the directive, and an optional list of clauses. In higher level pragmas, to tell the compiler to identify potential parallelism and handle the parallelization with the hash pragma ACC kernel pragmas. Apart from this, there is a parallel directive which requires analysis by programmers to ensure safe parallelism. So this is my code for matrix multiply, where I have parallelized the three loops. I have parallelized the outer loop in this matrix multiplication. And I have also compared it with different platforms like CUDA, OpenMP, and I've also performed the same code in single thread. So this is the comparison of runtime on single thread, OpenMP, CUDA, and OpenACC matrix multiplication. When the computation is large enough, a parallel approach will always be faster than single thread because the overhead of setting up the thread will be relatively small. It expected that the GPU outperforms CPU threads for large matrices. However, the above graph shows that OpenACC implementation outperforms CUDA. A straightforward technique was used for assigning one thread per row in CUDA implementation. The OpenACC compiler was able to optimize further by selecting dimensions according to the own analysis. As we can see from the graph, as the metric dimensional increases, there is a time in OpenACC decreases. And we can also see that in single thread, as the matrix dimension increases, time to run the program increases. So let's talk about benefits and limitations of OpenACC. So benefits: high-level platform, independent, simple, and portable. So OpenACC is wonderful solution if you need a quick implementation that can use GPU and is perform independent. However, there are limitations as well. However, you will never achieve the best performance possible at the lowest level of programming. This is true for almost every tool you might use, and is reality. Very few people will benefit from using much lower level tools simply because of the time taken to use this tool never paying off. As a programmer, we should always ask ourselves if it is worth putting in additional effort to optimize given the potential benefits, and how many times you might run the code and receive the benefit. Thank you.